Welcome to the first episode of the More Than Physics podcast. Here, just like in the text publication, I'm going to talk about physics, mathematics, science in general, but what I want to do here is frame it as a weekly report of my academic life. I'm currently taking a master's in theoretical physics, and I want to tell you what I'm studying, what I'm learning, what I'm struggling to understand, what the lectures are like, and what my study routine is. For a bit of context, I'm currently taking courses in quantum field theory, statistical field theory, and general relativity, which I'll sometimes refer to as just QFT, SFT, and GR. And my finals week is coming up. At the time of recording, I have a bit more than 2 weeks to prepare for the final exams for all these 3 courses. So without further ado, let's start with what I did this week. So my main focus was catching up with statistical field theory. I feel like I'm not understanding this course as much as the other ones, or at least that my intuition isn't as helpful here. And also this is the only course in which the final exam is 100% of your grade. For the other 2, there are some problem sets that we receive throughout the semester that we need to solve and then hand in, and they count for a bit of your grade, so there's not that much pressure in the final exam. I'm very much against this idea of making your whole semester depend on one test, but that's besides the point. My week started at the library, as it usually does, and the first thing I wanted to do was to take the book that this SFT course is based on to see what the topics for the finals were. I found out that everything revolves around studying properties of quantum gases, which are systems of many particles or many field excitations that move around and behave in different ways depending on what they're composed of. The 2 types that we're focusing on are fermionic gases and bosonic gases. Fermions are the particles that come together to form matter, so atoms, electrons, everything is made of fermions. And bosons are the particles that carry the interactions between the fermions. For example, the photon of light is a boson and the carrier for the electromagnetic interaction. The main differences in behavior for these 2 types of gases comes from the fact that for fermions, you can't have 2 of them occupying the same state. They don't like to be together. As for bosons, they don't have a problem with that, and in fact, sometimes they have a preference for it. Anyway, what we're learning right now is how to mathematically describe those gases and how to calculate their properties. We start by assuming that there's no interaction between the particles that compose those gases, and we describe their properties with techniques such as the semi-classical approach or something called the Matsubara sum or the Matsubara decomposition, which, to be honest, I have no strong idea of what it means physically to decompose fields in that way, but it is a very handy mathematical tool for these kinds of problems, so I kind of learned how the steps work and how to apply the process, and it's been kind of working. The last of these techniques or methods that we've encountered is called the Green's function method, which is very useful not only for this case, but also because it can be generalized for when we're actually dealing with the interactions between the particles of the gas. And the Green's function is actually something more general and pretty interesting. It's a neat trick to solve some kinds of differential equations. Most physicists will be familiar with that idea from their first theoretical look at electromagnetism. And here, the powerful thing about it is this Green's function describes exactly how a particle or a field excitation moves from one point in space-time to another. We call that a propagator. And this is where we can take the step towards interactions, because these Green's functions can be calculated for free fields or free particles, meaning they don't have anything in their way, or also for interacting ones, depending on what their environment looks like. Interactions are tricky and usually make things exponentially more complicated. In this case, we go from a situation in which it's possible and usually pretty okay even to calculate what happens with these gases immediately to a level of complexity and absurdity that is frankly immoral. We should call somebody. This is not okay. Treating almost any interacting case even remotely realistically is so unthinkable that we come up with a ton of approximations and assumptions, anything we can do to simplify things. There's so many integrals involved that are so big and complicated and actually really similar to each other so you can confuse them, that what people did is they started representing those integrals with drawings. They're called Feynman diagrams. Look them up, they're very interesting to look at, and I'm very thankful that they exist because I don't know how we would solve these problems otherwise. And that's when I kind of stopped my studying. There's one last thing that we do still need to know for the finals, which is phase transitions, but I haven't got there yet, so I will talk about that later. By that point, I was having some difficulty seeing the bigger picture, how things relate to each other. So I started taking separate notes about each concept or technique and then trying to connect those to each other to see what the relationships are, what the similarities, what the differences are, if there's something I can learn from one that can help me understand another, and so on. This ended up not being that helpful, so I changed my approach and started applying the universal technique of efficient studying in physics, which is basically just finding exams from previous years for the same course, trying my hand at exercises, and seeing where I get stuck. If you study maths or physics and you haven't tried this, I can't recommend this enough. It's incredible how this immediately shows you where your weaknesses are. And if you have an idea about what the material means, as I had due to my superficial reading of the book earlier, you can find where the explanations are for the things you're trying to understand. The main difference between doing this and just solving the problem sets related to each lecture is that, first of all, these exams tend to be very similar to each other, and therefore you can have an idea of what your final exam or midterm exam will look like. And these exam questions tend to be more broad and cover more subjects in one question. So instead of doing a bunch of problems for each section of your material, you can do a couple problems that kind of go through everything, and then you can see where your weaknesses are, and then you go to this specific section and do the practice problems. That way you can go deeper into what you're currently not that good at. This whole bit of studying that I just described took me a few days. I think I made some good progress, but I still want to devote the next full week to that course, to just going deeper into SFT, because I still believe I'm quite behind. There's a lot to understand and I don't want to risk it. That being said, I had to put a pause in my efforts for a few days, starting on Thursday, because we just received the last problem set for general relativity, which means if we solve those problems and hand them in, it will count as part of our final grade. These usually take about a week to work through, with a lot of conversations with other students and some group effort, but I was still feeling like I was really behind in statistical field theory. So I wanted to just lock in and finish that problem set as quickly as possible so that I could get back to that. So the problems were about some interesting spacetimes, namely, first we had to find some properties of the FLRW metric, which is basically a way to adapt our coordinate systems to the fact that the universe might be expanding. And by the way, a recent paper in cosmology seems to have a nice alternative to what we thought was happening to the expansion of the universe. It's called Supernovae Evidence for Foundational Change to Cosmological Models by Seifert and others. I do recommend the read. But anyway, after that, on another problem, we had to use something called the Komar integral, which is a method to calculate conserved quantities in general relativity to find expressions for the mass, electric and magnetic charges, and angular momentum of some rotating or charged black holes. It's very interesting, but it was very difficult. I'm happy to say, however, that by the time of recording this, it's Sunday night and I've finished it. Meaning I can forget about GR for the next week while I dive back into SFT and hopefully come out of it more prepared for the final exam. Overall, I'm happy about how this week went. I think I made some good progress in the courses that I wanted to. The lectures themselves weren't that interesting. We're just going deeper and deeper into the things that we've already seen, which I'm happy about because then we have time to solidify our knowledge and prepare ourselves rather than trying to shove more content in. As I mentioned before, my plan for next week is to keep doing exercises in statistical field theory to see if I can get a better grasp of it, but I'll also have to probably sprinkle in some quantum field theory as well, which is a course that I'm very much enjoying, but it's also quite complicated and that final is going to be difficult. So why not merge them both? Because statistical field theory and quantum field theory have a lot to do with each other. So that's a positive thing because when you study for one of them, you're actually preparing yourself for the other one. The concepts are very similar, even though in statistical field theory, you're dealing with many bodies. And in quantum field theory, we're going deeper into how the fields themselves work and interact. But many of the methods are very similar. So we're also using Green's functions. We're also using something called Feynman diagrams that I also mentioned earlier. But yeah, I do have to go to the exercises from the course of quantum field theory specifically to see what the similarities are and what's different between SFT and QFT. Because of course I can't just prepare myself for one of the courses and hope that the knowledge brings me a good grade on the other one as well. As for GR, I think I'm going to leave that aside for now and just have a refresher when the exam gets closer, because I think that's a subject that I'm more used to. I wrote my thesis about black holes, and so I have a bit of experience in that. And also, it's a course that it's more intuitive. So if you know the maths behind it, which I feel like I do, you can kind of wing it on the exercises. And also, there have been a lot of hand-ins, a lot of problem sets that we've handed in, and that composes a big part of our grade. So that means this final exam is not going to be that much of an importance. We do still need to do it, of course. We do still need to get a good grade on it, but I'm comfortable leaving this GR refresher to later, to at least the few days before the final exam. So yeah, this has been the report of my academic week, my plan for the next one, and the first episode of the More Than Physics podcast. Thank you for listening. I hope you enjoyed it. If you have any suggestions about how this format should evolve, or questions about any aspect of my academic week or my life at uni in general, I'll leave links in the description directing you to how to contact me. You can send me a DM on Blue Sky, write something in the chat or in the comments of the written publication, or come watch me live on Twitch, where I answer your science questions and we learn about the world together. Again, all that information will be in the description or the show notes. I don't know what the terminology is for podcasts, but again, thank you for listening, and until next time.